Hi, this is Dane Quinn from the University of Akron, and today I'd like to do an example with polar motion. We have a particle given here that moves along a helical path. So that path is defined as the radius in terms of the angle theta subtended by the path. So r of theta is some constant, k0, plus k2 times theta squared. So again, this path increases in radius quadratically with increases in the angle. Now, if the angular velocity is constant, right, so theta dot is omega, I'd like to find the position and velocity of the particle as a function of time. And in addition, we'll assume that the initial angle is 0. So here, let's identify the position of this particle, P, with respect to the origin O, as r of P with respect to O. And because the radius is given in terms of the angle, it's natural to use polar coordinates. So, of course, identifying directions I and J as fixed in the ground, then we can identify a direction ER and a direction E theta related to these through the angle theta subtended by the particle. So here, the position is given in terms of the ER direction. Right? So the position here is r of P with respect to O, is r, again this radius, which depends on the angle, in the ER direction. In addition, because we're using polar coordinates, we can immediately write down the velocity in terms of r and theta, as the velocity of P is r dot, so how the radius changes in time in the ER direction, plus r theta dot in the E theta direction. Now these directions can be related one to another. So writing ER and E theta in terms of I and J, we find that ER is equal to cosine of theta in the I direction plus sine of theta in the J direction, while E theta is equal to minus sine in the I direction plus cosine of theta in the J direction. Likewise, we can express I and J in terms of ER and E theta. And doing so, I would be cosine of theta in the ER direction minus sine of theta in the E theta direction, while J is equal to sine of theta in the ER direction plus cosine of theta in the E theta direction. So now, in terms of the angle theta, again the inclination of the particle with respect to horizontal, we have ER and E theta in terms of I and J in terms of ER and E theta. Now we'll point out that this angle continuously increases. Right? So after it goes through one revolution, the angle is 2 pi, and then the second revolution, the angle continues to increase, so at this point it would be 4 pi. And further increases just continue to increase this angle. So here we don't consider theta to be just between 0 and 2 pi. It can actually increase to values beyond 2 pi. And so, as a function of time, we can solve for theta, because our problem statement gives us theta dot is equal to omega. And then we can integrate that to find theta of t. Right, so let's do that. Theta dot, and I'll use tau as a dummy variable in the integration. Right, but theta dot, tau, is equal to omega. So again, if I integrate that from 0 to t with respect to tau, we end up with the following. Theta of t is simply omega t. And I'll remind you that the initial value was 0. So again, when I integrate the right-hand side, I just get the argument, because this is the integral of a derivative. So I get theta evaluated at t minus theta evaluated at 0 equals omega t. Now, in addition, we can solve for the radius as a function of time and r dot as a function of time. I'll look back and notice that the velocity depends on both r dot and theta dot. So here, r of t was k naught plus k2 times theta of t squared. So, since theta is omega t, we simply have k naught plus k2 times omega t squared. Now I'd also like to find r dot. And to do this, I'm actually going to use the chain rule. I could take the derivative of this with respect to time directly, but let's instead, for this example, take the chain rule. So again, r dot is the derivative of r, which is a function of theta, which is a function of t. So the derivative of r with respect to time is dr d theta times d theta dt. Again, this is the chain rule. And we can easily evaluate each of these separately to find that dr d theta is 2 times k2 times theta, right, just taking the derivative of this with respect to theta, times d theta dt, which again is theta dot. So now, looking at this expression, we find that r dot becomes 2k2. Here, theta is omega t, and theta dot is simply omega. So we end up with omega squared times t. Notice that the radius increases quadratically in time, and r dot, derivative of the radius, increases linearly in time. And this is exactly the same result that we would get if we simply took the derivative of this with respect to time. So finally, we can solve for the position and the velocity. R of p with respect to O, again this is a function of time, is, according to polar coordinates, r dot in the ER direction. And remember that ER changes in time as well. So r here, from this expression, is k naught plus k2 omega squared t squared times ER, or in the ER direction. And so finally, using our relationship for the directions, ER is cosine of theta I plus sine theta j. So when I take that and introduce it here, we end up with the following. The position is this magnitude, k naught plus k2 omega squared t squared, times cosine of theta, but theta is omega t, in the I direction, plus in the j direction, again the magnitude, k naught plus k2 omega squared t squared, now sine of theta, or sine of omega t, in the j direction. And then, looking at the velocity of this particle is r dot in the ER direction plus r theta dot in the E theta direction. Or, again, using all of this information that we have determined previously, 2k2 omega squared t, right, because that's r dot, in the ER direction, plus, now, k naught plus k2 omega squared t squared times omega is theta dot, in the e theta direction. And so finally, writing this in terms of I and j, we have a component in the I direction from ER, and we have a component in the I direction from the e theta direction. In the ER direction, that component is cosine I. E theta gives us minus sine theta I. So putting everything together, we have 2k2 omega squared t, and then cosine omega t. That was this in the I direction. In the j direction, we end up with minus k0 plus k2 omega squared t squared times omega sine omega t. And that again is the component in the I direction. And then in the j direction, we have 2k2 omega squared t times sine omega t. So now we're taking ER in the j direction, and we'll take e theta in the j direction. k0 plus k2 omega squared t squared times omega cosine omega t in the j direction. So finally, we have expressions for the velocity. Let's highlight that in blue. And the position. And we'll highlight that in blue as well. So once again, the position as a function of time can be given as this expression, and the velocity as a function of time in the I and j directions are given here. So this is an example with polar coordinates where the path is known, and in particular the path was given to us as the radius as a function of the angle. And then from that we were able to deduce the position and the velocity of the particle. So that's it for this example. Thank you very much, and I'll be back.